All right, so I want to construct a shear force and bending moment diagram for this guy. Now, you might remember that at the beginning of the semester, we talked about these triangular loads, that they're not necessarily designed to torment you as a student, but they actually have a rationale in the way the tributary loads are applied from slabs, roofs, things like that. So it's not a terrible one. You'll also notice that the load is applied continuously throughout the whole structure, so that might be an advantage. So starting with the same process that we've been doing previously, I'll go ahead and assume that I have a positive shear at A and a positive shear at B. And those are my positive sign conventions. To find those values, I'm going to need to resolve this distributed load into a concentrated equivalent version. So I'm going to indicate that with a double line. And I know that the concentrated equivalent version is the area under the curve. Well, it's a triangle, so that's going to be easy. It's 1/2 base times height, so 1/2 18 times 4, that should be 36. And the centroid of a triangle is 1/3 the base distance from the larger end. So 1/3 of 18 is 6 feet. So I should have everything I need to find my reactions. And since I've already based my distance to the centroid from B, I think I'll sum my moments about B. I want to make sure my body is in equilibrium. So I'll start by summing moments, making sure they're 0. And I'm going to pick B to do that. You could pick A if you like. Again, I'm using right-hand rule. So about point B, this concentrated equivalent force creates what kind of moment? Positive. So I've got a 36 kip force. And the distance from B, we've already established that. That's 6 feet. My shear at A creates negative moment. It'll have a force of the shear times that distance, which is 18 feet. So it's not hard to find that the shear at A is 12?
Yes.
12 kips, and it's positive, so I have a positive shear at A. Now, since I have one of my vertical forces, I can just sum forces in the y direction and make sure I'm in equilibrium to find the shear at B. So I'm going to assume up is positive. So starting at A, I've got a positive force that's up, so that's shear at A. I have a force that's down, that's the shear at B. And my 36 kip force is also down. That's my concentrated equivalent. So I should be able to find the shear at B, and it looks like it's going to be negative 24. So I've got a negative shear at B and a positive shear at A, as you can see by my sign conventions. All right, so let's draw a template. I'll start with on my left side and extend to the length of the beam on the right-hand side. I don't see anything in the loading between A and B that would indicate that I would have anything ahead of time that I would mark. So I'm just going to leave that blank for right now. But I will add that I'm going to assume positive X, positive shear, and all my shear values will be in kips. So starting on the left-hand side, what's my shear? Well, it's the shear at A. The shear at A is 12. I also know the shear at B. What is it? Negative 24. So again, I know where I'm starting and know where I'm going. Remember, our basic relationships are change in shear is equal to the area under the load curve. Let's do that one first. Looking at the load, you can see it's continuous throughout the whole span, so I can take the total area of the curve. Remember, it's a triangle, 1/2 base times height. We've already done that. That's how we came up with the concentrated equivalent of 36. Is that a positive load or a negative load? It is negative. So 12 minus 36, it is 24, so that works. The slope of my shear diagram is equal to the load. Let's go see what the load is. So starting here at A, what's the value of my load? It is 0. So that means I have a 0 slope. And the slope increases to a maximum value of 4 here at the end. Is that a positive or a negative value? It is negative. So that means I have a negative slope. In fact, if I marked it, it would be 1 to negative 4. So this is a linear curve. This should be a parabolic curve. So let me see if I can sketch something that fits in there. Something like that. Now some issues pop up. We crossed the axis. We went from a positive shear, this is positive shear, to negative shear. Somewhere there I cross the axis and I have 0 shear. And we know that's going to be important because what is that? That's probably going to be where my moment is going to be max or min. Now this is where I'm working this problem kind of intentionally at the beginning because I want to kind of show you this is where this graphical technique of shear force and bending moment kind of hits a little bit of a bump. All right? When I go to draw my moment diagram, so I'll go ahead and assume positive x, positive moment, and I'll do kip feet for my values. I know that at A I've got no moment, and at B I've got no moment. But this positive area under the shear diagram, we know that the change in moment is equal to the area of the shear diagram. So this positive area will make me move up to some value. And in this negative area will probably bring me down to 0. Seems reasonable, right? And I also know that the slope of my moment diagram is equal to the value of the shear. The tricky part is, how do I calculate this area underneath the curve? Yeah, It's not so easy. Now, it just so happens that this little segment here is a parabolic segment because we know it's a parabola because this is a linear line. When you integrate it, you get a second order curve. So it's a parabola. And since we have a 0 slope, this is a parabolic section. So whether you remember or not, the area of a parabola or a parabolic section is 2/3 the base times the height. There's the height. Oop, I got to find the base. We'll come back and do that in a second. So I could find that area. What about this side over here? What's that? I have no idea. That's just a segment of a parabola, right? It's not a parabolic section. You notice it doesn't start with a slope of 0 or end with a slope of 0. I don't know how you'd find that, to be honest with you. So that's where this method kind of breaks down. When you stop being able to easily find areas under sections of curves, then this graphical technique kind of breaks down. So if I gave you this problem, I would be tempted to tell you to write an equation for shear and moment like we've done before and just plot them. Because we've worked this problem. We've written the equation for shear and the equation for moment. And this is one continuous function, so it wouldn't be challenging to do. So that's kind of where it breaks down. I'll show you as far as I think we can go. What is this distance x1? Well, if you project that up, right? Let me see if I can find a different color here. And I look at the area under the load curve, right? So if that distance is x1, this distance is x1. So according to my my scheme here, the change in shear is what? What's the change in shear from here to here? I start at 12, I end at 0, so the change in shear is minus 12. What's the area under the load curve on that same distance? It would be this area here, which is 1/2 base x1 times height. Ooh, what's the height there? What's the slope of this line? Rise over run. 4 divided by 18. That's 2/9. So this would be 2x over 9. That will tell me the height. Actually, I'll put x1 there. 2x1 over 9. See that? So what's the area of the curve going to be now? 1/2 the base times the height. The 2's cancel and you get x1 squared over 9. These two, oh, I messed up too. This is a -4, so the whole thing is negative. If I take that relationship, let me bring it down here so I can solve it. So it ends up saying that x1 squared over 9 should be equal to 12. So if I multiply both sides by 9, I get x1 squared is equal to 108. And if I take the square root, what do I get? 5 something. 5.2?
10.4.
Oh, I'm sorry. Yeah, 10. 10.4? I was doing half of it. So I know that part of the curve is 10.4. You may or may not remember this relationship, but if you did, then what would be that area? It'd be 2/3 base, x1, which is 10.4, times height, which is 12. What's that? So 2/3 times 12 times 10.4.
I got 83.2.
80 what?
83.2.
That sounds reasonable. Anybody else get that?
2/3.
Okay. 83.2. Now, if you look at the slope, we start off here. Our shear value is a positive value, and it decreases to 0. So I know my slope is 0 here and some positive value here. I could sketch in that part of my moment curve. And this is kind of where my whole process definitely comes to a halt, because I don't know how to find the area of that part of the curve. Hopefully it would be negative 83.2 and bring us back to 0. And I may have also discovered my maximum moment and where it occurs. My maximum moment is 83.2. Where does it occur? 10.2. So if that's 10.2 feet, this is going to be 10.4. So this is going to be 7.6. That's kind of where I have to kind of crash and burn. Now, to remind you, if you get in this jam in homework, let me show you right here. This is the back of your book. And this is a parabolic section that we just talked about. You can see it's a parabola, and there's definitely a 0 slope. You could imagine it also this way, where it really looks like a 0 slope in this direction. And when you do that, you can see the area is 2/3 base times height. Now, the opposite of that is if you made a rectangle here and you look at that little remaining piece, that's called a spandrel of that. And, of course, that's the remaining 1/3 of the base times height for the rectangle. Now, that's for a parabola. If your curve is higher order, then these are the same functions. And you can see it's a function of n, which is the order of the curve. If it was a cubic curve, n would be 3. I don't expect you to remember those. I've done this long enough that I can kind of remember this part of it, but that's about it. So since I'm not going to let you use your book on the exam, I would probably not expect you to have to deal with one of these on the exam. If I did, I think the most logical approach would be to use method of sections, write your equations for shear and moment, just plot them. Now, it might be a little more challenging finding this maximum value and where it occurs. So, I just thought I'd throw that out. I don't want to make everything seem perfect, like drawing shear force and bending moment diagrams is absolutely the best thing ever. It's close, but not the best ever. There are some issues. All right, we'll stop.